Now, in terms of the numerical example we've just seen, I'm going to say that the integral over the closed curve of f dot dr, which is the integral over the closed curve of pi plus qj, where p and q are functions of x and y, two variables, dotted with dxi plus dyj. Whatever curve you use, dr is, if r is x of ti plus y of tj, then dr is dxi plus dyj. Now that might be dx dt times dt plus dy dt times dt, times I and j accordingly. But that integral then becomes the integral p dx plus q dy. And in keeping with my admonition to always use parentheses to indicate grouping, I should have put parentheses around that, we get this integral. And in terms of what we've seen, this is the integral over the entire region, okay, of negative py plus qx integrated with respect to area. Now this will generally be a double integral because the region is a region described in two dimensions, and the area increment is a dy dx or a dx dy. And it could also be an r dr dt, depending on how you do the integral and how you set up the function. Okay? So you have the negative py dA that we've seen and the plus qx dA that I've alluded to and showed you in part. Okay, now the numerical example I gave you is not a proof, but it's a very good plausibility argument. The proof is in your text and it follows exactly the same kind of reasoning we used with the numbers. And if you don't relate well to numbers but relate better to symbols, you'll understand the symbolic integral probably better than you do the numerical approximation. Okay, now there's more to it than this, and I didn't mention it in class. We only did the integral over one tiny rectangle. If you have a complete path, you can pretty much break that path down into tiny rectangles, and integrating clockwise around each of the tiny rectangles, you cancel out everything except on the outer boundary of your rectangles, and you see that in your textbook. I didn't talk about that in class because it took us quite a while to even evaluate the functions. We spent more time with that than I expected. We didn't have time to get to it. I'll probably do a video on that, but of course I've already got videos that show you that. Made a few years ago. Okay. Anyhow, I call this the astounding big deal theorem. The biggest theorem you've seen in this course probably. Of course, the fundamental theorem applied to conservative fields and all that stuff is pretty astounding and pretty big too. But this is even bigger, if that's possible. This is called Greens Theorem. It allows you to evaluate a line integral by doing an area integral. Sometimes it's easier to do the area integral than it is to do the line integral. It allows you to do an area integral by doing a line integral, if the area integral has a certain form. So it's a very powerful tool just in that right. It also allows you to do flux and circulation integrals, which are extremely basic to hydrodynamics, electrodynamics, electrostatics, and numerous other fields of engineering, fields that are important in engineering, fields that are important in physics, and fields that are important mathematically. So this is a big deal, and we're going to see how big a deal over the next couple of weeks. Now I do one example. Okay, I do the integral of x squared I minus x squared y squared j dot dr over the unit circle. Okay, well, we parameterize the unit circle by r equals cosine ti plus sine tj, t running from 0 to 2 pi. Now hopefully we understand, and when we talk about the unit circle, we automatically think of this parameterization and some alternative parameterizations. Okay, this is not the only possible parameterization, but it's the one that's often most convenient. Now, by this parameterization, we know that x is the coefficient of I and y is the coefficient of j, so that x is cosine t and y is sine t. So we translate these x squared y and x squared y squared expressions into cosines and sines, and that's obvious. And we dot that by the dr. Okay, what's the dr? Well, it's just the differential of this. It's the derivative of cosine t times dt plus the derivative of sine t times dt. It's negative sine t dt plus cosine t, well, negative sine t I dt plus cosine t j dt. Our dot product, then it becomes what you see here. And that's it. That's the line integral. Now there's also an area integral, and I thought I was going to do that, but I didn't. So I'll just kind of write that down here. The corresponding area integral is the integral of what? Well, p is x squared y, so py is just x squared. Now it's negative x squared, okay? And then qx. Q is negative x squared y squared. Qx is then negative, I'm sorry, I changed this to a minus. My original function was plus, so I'm going to go back to my original function and just change those three signs. Okay, then I've got a plus x squared y squared j. Okay, my qx is then 2x y squared. And that could be with respect to y and with respect to x. Now, if we integrate with respect to x last, the unit circle, and you should know this, has limits -1 and 1 with respect to x, if you're using x as your outer integral, and your inner integral with respect to y is from negative square root of 1 minus x squared to the square root of 1 minus x squared. Okay, this would be the corresponding integral over the area. And we can perform this integral quite easily. We do get into some trig substitution. It's more or less equivalent to the kind of trigonometric integrals we do down here. But this and this should end up equal. So you can do those integrations, check that out, and see if that's really the case. Okay, now, and we'll do this in another video, we're going to do the double integral of qx minus py dA for, well, you know what? I thought that this was associated with this, so I just wrote this out, but right here it is. Okay, same integral, except that I changed my q to be a positive x squared y squared, so I'm going to have a positive here. Okay. Now the next thing we want to do is figure out how to do an area integral for the area of this ellipse. So we're going to proceed with that in the next video.